Is this any better? Mildly, if at all? All right, let's mute. Is there any improvement? Hello? Maybe. Testing. Okay, well, it appears to be on, but I have to hold it like a centimeter from my mouth, which I think at this stage is not a good idea. Okay, well, we'll see if it happens on I will tell you. Okay, hopefully this will be okay now. I'll try to suggest. All right, well, welcome to the Friday before spring break. I know that I am one of the classes that you have that things you new and the beautiful weather that we have outside. So I'll try to keep it succinct. We'll be wrapping up a Conductivity today, which also means we'll wrap up the modules that are covered in the exam 2. And to give you all ample time to prepare for exam 2, I will go over some of the terms and conditions like I did for exam 1, just so we're all very clear. Although in retrospect, maybe the second exam for the first break is not the most ideal time, but I would have given this, to keep the same pace, I would have given this next Friday, because we're not here next Friday. I thought I'd do it too early, and that way all the information is there, and you can do this okay? So I think we can just get, well, I don't know if we want to get that out of the way. Let's do electronic copy first before we discuss these. And if you just got here, we are taking attendance for this much smaller class size today. So here's your chance to ask, questions and such. This will be better. Okay, fabulous. Okay, so Dr. Boudin introduced the concept of band gap and how we discuss conductivity and also resistivity. And so we'll be focusing a lot today on basically semiconductors and how do we make them, how do we manipulate them by
by doping, by basically intentionally adding impurity atoms and manipulating the charge carriers and how they behave in the material. And this, of course, has profound effects on the conductivity of the material, right? And just by adding a fraction of the number of atoms that are available in the parent phase of the material, you can really dramatically increase conductivity. So silicon by itself, the intrinsic semiconductors, silicon by itself, conductivity is not that high, right? It's an okay semiconductor, but it doesn't conduct very well. But by just adding, honestly, like much less than 1%, like 0.1% of a dopant atom, you can drive the conductivity up by an order of, multiple magnitudes of order. So you can increase it by like 1,000 times just by adding in some small number of dopants. I want to go over band gaps and band structures to review so that we're all familiar again. So Gary introduced the concept of how atoms come together and form a band structure. Right? He gave the example of if you have different atoms in free space, you have some discretized atomic energy levels. And then when you pack all those atoms together in the solid state, you have a band because all those energy levels are now packed together, and you treat the material as a whole and discuss its band structure. And so band structure, if you're already in ECE, I think you're quite familiar with this because this is what you manipulate in terms of the material properties that you desire. But if you're not, we'll go over it in greater detail so that we're all on the same page. So by choosing materials, right, that have a certain type of band gap or certain optical properties, we can decide how materials, what sort of application we can use it for. So the example that I gave several lectures ago on chromium or chromia, so chromium oxide, doped alumina, right? That alumina is an insulator, but you can introduce some certain bands, some certain states in the middle here, certain energy states that are in the middle by introducing these dopants. So introducing chromia, so chromium oxide doping. And because it affects the band gap, it also affects how you view the material, what color you see, what colors are absorbed and what colors are emitted, or wavelengths that are absorbed and wavelengths that are emitted. That affects how, the color that you see in the material. And we can calculate all of this, but if we know the concentration of the dopant, we can calculate all of electronic properties of the material. If we know the properties of the material, so we can just measure, do 2-point probe, 4-point probe, however you want. We can do electronic property measurements and then also backtrack the concentration of the dopant once we know the intrinsic properties of the material, of the parent phase. Right? So of course this has huge implications not only in the electronics field, given that it's electronic properties that we're talking about, but it also has huge implications in the in optics as well. Okay, so a lot of the crystals that one can buy, single crystals that one can buy for laser spectroscopy, it's based on really manipulating the electronic properties in these materials. Let's see, what else? What other example? Oh, the two types of metal connections, the single phase and two-phase. Well, certainly, what do you mean by better? Well, it all rests in how easy is it for you to go as an electron, as a charge carrier, to go from the valence band to the connection band where then you can conduct. Right? So it's overlapping like a transition metal. Your valence band, your shell bands versus your entry bands are overlapping. So there's really, uniformly at site, like at any given temperature, there's going to be electrons that are activated as you go into the field state. Now, for
things like lithium, sodium, right? They have potassium. It's one S1, two S1, so they have hostile states. So there's a portion of your valence bands that are empty because your S orbitals are empty. But that doesn't really matter because they're still metal. Lithium is a metal, sodium is a metal, they also stuff. So in terms of comparing these two for conductivity, it all just rests on how easy it is to get from the filled state to the empty state. Clearly, you know, since there's a small band gap here, to go from here to here, there isn't really any energy that one would need to be excited. Whereas in an insulator or a semiconductor, you would have to actually activate and excite the electron somehow. So if the electron is in this state, you need to overcome this amount of energy, right? That's the band gap, Eg. You need to overcome exactly that or more. So if you have more energy, let's say you shine some light on it, right? If you shine light on a semiconductor, light is really electromagnetic radiation, right? Light has some wavelength. So C is the speed of light, H is Planck's constant, so it's just a constant, and lambda is wavelength. Let's say it's visible, right? So it's between 400 and 700 millimeters. If you shine some light, you're actually introducing some sort of energy into the system, which you can actually excite. So I guess to answer your question, it depends on whatever your conditions are, you know, that you're designing for. But in general, it doesn't really matter because metals conduct. Okay. Part of your book goes into conductivity of polymers and ceramic materials. We won't go into that. We'll only discuss semiconductors for this class because as it is, there's already a lot of content that's packed in there. So I'm just going to focus on semiconductors for this module. Okay. We went through all of this. Right. Semiconductors. Let's talk about them. You'll be seeing the band structure diagram quite a bit. So semiconductors, they share the same property as insulator in the sense that there is a band gap. Now, what is the threshold between the band gap of a semiconductor versus the band gap of an insulator, right? How big of a band gap do you need to have an insulator versus a semiconductor? Well, you could think about dopability. You know, if I dope this material, how much of the conductivity am I going to improve or am I going to increase? Right, with insulators, it's really hard to do that. So generally, the rule of thumb is if your band gap is about 3.5 eV or more, or you know, larger number than that, that's going to be an insulator. I know in your book and in certain other intro textbooks, they'll say between 2 eV and above. It's really more like 3.5 and above. You know, it's not like, okay, if you're at 2.99 and then you're at 3 eV, now you're an insulator. It's not so much that clear cut, but generally, as a rule of thumb, if you had to have a cutoff for band gap, you know, I would say at least 3 eV for something to be considered an insulator. But what you're really saying when you call something an insulator is that it's not very conductive, right? It's just more resistive is what you're trying to communicate to somebody. But that's the general rule of thumb, is that there is a band gap for an insulator and it's actually very large. And that large band gap makes it difficult for electrons to be excited from the valence band to the conduction band where they can freely conduct in the solid state of your material. So of course, what that means is then there's no current, right? You need electrons to be excited to do so.
And so how do you have enough energy? It could just be thermal energy, right? Thermal vibrations, KT, you can just have enough energy at room temperature for electrons to be excited if your band gap is small enough. And with silicon, and germanium, their band gap of, so silicon goes about 1 eV, germanium is about 0.6, 0.7 eV. And so thermally at room temperature, there's always some fraction of the population of electrons that will be just thermally activated, thermally excited. But if you want a higher concentration and in a controlled way that you want excitation, then you're going to have to do something. You're going to have to introduce, let's say, a laser or something like that to add energy into the system, or an electric field even to drive the electrons to do so. So as I said, excitation is usually heat, also less commonly from light, but of course that's an external perturbation. You can just shine a light. And then what happens when you excite an electron from the valence band to the conduction band is you introduce what's called a hole, or an electron hole. So this hole is left behind when this electron that used to be here in this state gets excited to an energy state in the conduction band, right? So a hole is not a real thing. It's like not a physical thing. It's a mathematical concept, by the way. But we can assign concepts like mobility, like we do in the same way that we assign, the mobility to electrons, right? How mobile are electrons? We can say the same thing about the holes that they left behind, because that also gives us another metric to talk about in terms of the material properties of these semiconductors. Although, you're going to go and try to find a hole, it's like not actually a physical hole, by the way. It's a particle state. So just FYI. So we call that the electron hole pair, or an exciton, right? Once you excite, you'll have an excited electron and then a hole. So that's your exciton. And they can move in opposite directions if you applied electric field, right? Electrons will go towards the positive side. The holes will go towards the negative side because they have opposite charge of electron charge. So that's one. The other option that can happen is they'll just recombine. So you have what's called carrier lifetime for this reason. So once you excite an electron, you leave behind a hole, but then at any given time, right, the electron can just relax back. It's at a higher energy state. So what it's going to want to do is relax to a lower energy state. And when that happens, that's called recombination. And then you no longer have an excited electron that's going to conduct. So what people typically do when they're engineering PN-type junctions or semiconductor devices is they'll actually try to increase the carrier lifetime so that so that the device works in a certain way. Okay. And then when actually electrons recombine, they actually emit some light. So h nu being frequency. Well, so h nu is the same thing as c over lambda, the frequency. And so all that does is it'll emit some light, and that's the light that you see. Right? That's the color that you see when electrons recombine, relax, and emit some color. So every single material that you see, whether it's white or black or blue or green or red in the case of ruby, that's all because things are emitting, and this is what wavelengths are being emitted and wavelengths are being absorbed, and that's what you see. Okay, so it's pretty fun to work with materials when you're trying to engineer new materials. You think, okay, what wavelengths do I need, things like that. This is where it comes from. So you look at the band gap property, band gap of material. So you can look up in these databases, or you can also invent new materials and engineer new materials as well. Okay, so there you have it, the animated version of exactly what I just said. So in terms of electron hole, as I said, the free electrons have a certain charge, right? And that's negative 1.6 times 10 to the negative 19 coulomb. And so thus the charge on the hole is the opposite of that. It's positive 1.6 times 10 to the negative 19 coulomb. So when we talk about conductivity and mobility of either an electron or a hole, you typically see, right, the number of charge carrier, the charge, well here, generically it's written as Q, but it's the absolute value of that. And then it's the mobility of that electron or hole, or sometimes both added together if you have an intrinsic semiconductor, right? I should also emphasize, just because it's oppositely charged, it's actually not a proton, it's just a hole, okay? And the way electrons move throughout a lattice versus holes moving throughout a lattice, so electron hole. So when I shorthand say things like a hole, I really mean an electron hole, okay? When holes move through lattices versus when electrons move through lattices, they don't move at the same rate. They have the same charge, magnitude-wise, but they don't move at the same rate. So what you'll see in data tables in your book and elsewhere is that mobility for electrons tends to be higher and holes tend to be lower. Okay. And also when we talk about semiconductors, we talk about these charge carriers, right? These charge carriers and that contribute to the conductivity. And so there are intrinsic charge carriers and there are also extrinsic. So there are intrinsic semiconductors and there are extrinsic semiconductors. Most of the material that you will encounter in your life in electronic devices are going to be extrinsic semiconductors. All that means is that somebody has engineered a material with some amount of impurity built in, right? And either they've added elements that have fewer valence electrons or more valence electrons than the host material. So the classic example that your book uses a lot and a lot of the intro classes use as well is silicon. For a good reason, it's industrially relevant. There's been a lot of studies done on just the properties of silicon itself. And a lot of times we're talking about single crystal silicon because that's what's used in all of these semiconductor devices. And so in the intrinsic semiconductors, we talk about the electrical behavior as it's based on the electronic structure that is inherent to the pure material. So when we talk about silicon, I'm talking about the intrinsic properties of silicon. We haven't done anything to it. There may be some impurities just because of the way manufacturing works, right? We can't ever have 100% absolutely pure materials as much as we try, but we try, and the best material that we can ever make would be, would have impurities on the level of like 10, less than 10 to the negative 6 weight percent. I mean, extremely, extremely low, but you'll never actually get something so pure. And these impurities could be vacancies, they could just be a random atom that wasn't purified out. When we talk about intrinsic properties as well, like copper, even though it's a metal, right? When you buy copper, just like from Home Depot or something, that's just like your generic grade copper. But if you were doing research using copper or you were engineering some device that uses copper, what you really want is like low oxygen content. And in fact, it's like called oxygen-free, high purity copper. So you'll see that if you go to a chemical vendor and you buy this like very specialized pure copper, it's going to cost you way more than if you went to the Home Depot than to buy your copper for whatever it is that you need it for. And that's because somebody spent a really long time purifying and extruding and making pure material. So making pure intrinsic semiconductors is actually extremely difficult. And the example that I've been using throughout the class so far has been, Intel and its process on how they make single crystal silicon. I mean, clearly it's $1 billion industry, so people really care about how pure silicon is. And they spent a long time figuring out which sand will best reduce from silicon dioxide to silicon to then go into all of your devices. Okay? So this in itself, while the conductivity is low, and ultimately we actually will introduce impurity atoms so that we can engineer a semiconductor device. The starting point is an intrinsic semiconductor that is very pure. Okay. So classic example would be silicon, germanium as well. So here's the lattice for pure germanium. You have all the germanium atoms, and they're bonded in some way by these blue bonds that are here. And then if there's some excitation, let's say there's just thermal excitation, all right? So a little bit of heat, even at room temperature, there's going to be some electrons. So each of these bonds have has 2 electrons in them, right? And so if there's thermal excitation, then one of the electrons can just escape out of that. Why not? I mean, statistically, it's absolutely possible with thermal vibrations, right? So when that happens, if an electron is excited, a hole is left behind. So that's shown here in the schematic. But when you apply an electric field, right, if this is the positive side and this is the negative side, then the electrons are going to be attracted to the positive end, and the holes are going to be attracted to the negative side. And so you can actually direct the motion of these electrons. But this is an intrinsic semiconductor. So the number of charge carriers that you even have, so the number of these electrons and holes that you have are quite low, okay? Because to escape one of these bonds is difficult, right? Because as we learned from atomic bonding module 2, once you make that bond, it's pretty happy. It's in thermodynamic equilibrium. It's not really going to want to leave. So that's when you have to introduce impurity atoms that have more electrons or fewer electrons to drive this motion, which is exactly why Intel is a business as a whole. So some information about intrinsic semiconductors. So pretty small band gap. Silicon is about 1 eV, germanium 0.67, 0.7 eV. So these are just elemental semiconductors, right? They have a band gap, they're single element, but you can also have what's called compound semiconductors. And here's an example: gallium phosphide, cadmium sulfide. You can have gallium arsenide. That was huge in the 90s. People did a lot of research on gallium arsenide. And all that means is you have now a cation and an anion. So you can absolutely have a compound semiconductor as well. They have band gaps. Cadmium sulfide here is 2.5 eV. Gallium phosphide 2.25. Gallium arsenide also a semiconductor band gap. And when you excite the electron from the valence band to the conduction band, you have still an exciton, right? You have an excited electron that leaves behind a hole. So that's fine. So how do you count the number of charge carriers? How do you count what's contributing to your conductivity, right? So when you're counting for what this is, you have to now consider the mobility of your electron, the mobility of your hole. But how do you count the number of charge carriers here? When the number of charge carriers in your system is exactly that. When you excite one electron, it leaves behind one hole. So the number of electrons is the same as the number of holes. Right? So N is equal to P being representative of the number of holes. And so the intrinsic charge carrier number is just that. So whatever number of electrons that you excite, that's the charge carrier. Okay. Yeah. En. Oh, this. Oh, ES. Your Fermi level. That's just the highest filled state at 0 Kelvin. So that's the highest energy level for metals, and then for semiconductors, it's just defined as the middle of your band gap. Ooh, why is it not? Why would it be there? Like, why wouldn't it be at the top of your valence band versus at the bottom of your conduction band? Yeah, so it is called forbidden states. That's true. But when you start filling in, when you start adding in impurity atoms, you can actually generate states, energy states that are in the band gap. Yeah, that's a whole nother thing. So we'll get to that. So yes, intrinsically, if there's a band gap, you shouldn't have an energy state. Can you philosophically have an energy state? Yes, but I think that's way more down the rabbit hole than we want to go in for this lecture right now. But if there's a band gap, correct, there are forbidden states there. Yeah. Oh, as in like how many lines should you have? How many lines you should have is the number of atoms that you have in your system. So if you have some copper, and let's say you define your material as 1 cubic meter, right? The number of atoms that's in that cubic meter is the number, that's the big N. That's the number of states that you're going to have. So let's say you have sodium, right? S1. So half of your s orbital is filled. So if you have 10 to the 18 sodium atoms, you're going to have 10 to the 18 states. Yeah. Mm-hmm. Yeah, okay. Now, okay, that's a slightly different question. So I'll break it down into two. So how many states do you have? That depends on the number of atoms. What type of states do you have? And is it discretized? That goes back to the energy states that goes back to your electronic configuration. So hydrogen would have one S state only, right? I mean, two S is unfilled, two P is unfilled, yada yada. And then the next one up, helium, it would also only have one S state because it's one S2. That's it. So the energy orbitals, the energy, the energies of the orbitals are dependent on your electronic configuration of the atoms themselves. We'll come back to it. Yes. This is an E for electron. That is an H for hole. Yeah. Yeah, so here when we talk about the band gap, we're really just talking about the valence band. So like when we talk about carbon, we're really talking about the 2s, 2p states. Because they'll hybridize and they'll make, that is your valence band, or that's your valence energy level. And that's when all these atomic orbitals come together, they make the solid band. At least the formalism by which we discussed energy levels. Yeah. Oh, yeah, I see. Yeah, I understand your comment. I should clarify and say that when we talk about like solid state, so here I've shown the discretized, like here are all these energy levels for every single atom to the nth atom. In reality, that's not actually how that works, right? In reality, we treat these bands as bands. Like we just take it as a whole. Like when you read papers or when we just discuss electron property theory, we don't actually like draw all these states. All we do is just say, we'll talk about these states, but as a whole. So what you'll see is we discuss this and this as a whole. Like we don't actually start discussing those states unless we start talking about the impurities themselves. And we'll get to that. Okay, so yeah, no, that's a whole electronic property story. But I do want to get some salient points across, and that is intrinsic conductivity. On Wednesday, you talked about how conductivity for metals actually decrease with increasing temperature, right? Because it's because you have all these scattering effects. right? As you heat up the material, it's not so much that the electrons just all propagate, right? It's not like you just give it more energy and then they'll just propagate and have higher conductivity, right? They actually start scattering off of each other, and the scattering effects actually decrease the conductivity. But for semiconductors, as temperature increases, your conductivity increases because your intrinsic carrier density also increases, right? So here you have increasing temperature, intrinsic carrier concentration is increasing, and so your conductivity will ultimately increase because your conductivity is dictated by the equation that relies on the number of charge carriers. So if the number of carriers is increasing, then ultimately your conductivity will increase because your mobilities are sort of increasing. Yes, mobilities change with temperature. They're not always so constant. The charge is not going to change, right? It's always 1.6 times 10 to the negative 19 coulomb. So what's really changing dramatically is your charge carrier. So as you increase your carrier concentration, you're going to increase the conductivity in your material. Okay. And how do you know your charge carrier? How do you know your carrier concentration is increasing? Because the carrier concentration is dependent on the temperature itself. Okay. So overcoming these hopping mechanisms, that's all lumped into the e to the negative band gap divided by kT. Okay. So increasing temperature, increasing conductivity for these intrinsic semiconductors. And it's all thermal excitation. So we're just talking about temperature, we're just talking about thermal excitation so far. And the takeaway message is it's absolutely the opposite of the behavior of metals. And because it's a Arrhenius type relationship where it's thermally activated, we can backtrack and calculate the band gap of the material by measuring the conductivity, right? So let's go back. If you measure the conductivity, what's hidden in your conductivity are all these terms about carrier concentration and also mobilities of your electron in your hole. And thus, if it's an Arrhenius type relationship, if you plot the natural log of conductivity as a function of reciprocal temperature, 1 over T, you see that it looks exactly like the diffusivity problems that we discussed in the diffusion module. Or rates of oxidation, things like that, they're all thermally activated. So then you can calculate what the band gap is by taking the slope of the line that you have. Yeah. The scattering events in metals will decrease the conductivity that you observe. So as electrons get heated up as well, right, they're flowing, but now they're also starting to scatter into each other much more so, and then it's actually counterproductive to increasing conductivity. Okay, so there you have it. We've done this type of problem before where we can calculate what the energy term is by taking the natural log of both sides and basically solving a system of equations to get, before we had vacancy formation energy, we also calculated diffusivity values. Now we can calculate band gap as well, and it all rests on the Arrhenius relationship. Okay. Let me come back to this example question so that I can lump in all the examples together in the interest of time. Okay, right. So I talked about your lives being dictated by N-type and P-type materials. So the type of impurity atom that you choose will dictate the charge carrier. Okay. It will dictate the dominant charge carrier. So whether it's going to be an electron or a hole, this depends on which element you pick based on your parent material. So for N-type, these are going to be donors. The impurities that you add in, the dopants that you add in are going to be donors. and that means they're donating an electron. So if you have a host matrix of just silicon, right, it has 4 valence electrons. If you add in phosphorus, you go 1 over to the right in the periodic table, there are 5 valence electrons. So here is the extra electron. Clearly, all the other electrons are going to be in bonds where there's 8 electrons around them, and it's nice, satisfies, Gen Chem, octet rule. That's great. Now, this extra electron, what it's going to do is it can migrate through the system, and if you apply an electric field, right, and you introduce some bias, the electron is going to gravitate towards the positive side and be able to migrate that way. Right. So this 5th electron is free, so it's not bound. And of course, the phosphorus atom has a +1 charge as compared to the silicon atom. And when we look at the band gap, now we're going to come back to your question, both of your questions, I think, about energy states in the forbidden zone, in the band gap itself. So the energy state of this extra electron, it's going to sit right below the conduction band, and it's called the donor state. So then if you look at the band gap, you can say, okay, well, I can excite this electron in the valence band up to the conduction band. I can also excite this electron from the donor state into the conduction band as well. So you can see that the energy levels are quite different, right? The amount of energy that one needs to overcome the band gap versus going from the donor state to the conduction band is drastically different, right? So that means you can easily excite the electron from the donor state to the conduction band, which is some thermal energy. Okay. Thermal energy tends to overcome this type of difference in energy. Similarly, so we went from silicon, we added some phosphorus, and went to the right side of the periodic table. Let's go 1 column to the left, right? So you can add in aluminum, you can add in boron, but they have 1 fewer valence electron. So in this example, I use aluminum, but boron will also have 3 valence electrons. And so that means then that here you can have a hole, and that will also migrate through the lattice. So now your dominant charge carrier is going to be the hole. And where is the energy of this hole? Well, the acceptor state, so the boron or aluminum doped into silicon is an acceptor. And the acceptor state is going to be right above the valence band. And so exciting a hole, exciting an electron from the valence band to the acceptor state is also going to be some small energy relative to that of overcoming the band gap. Okay. And just as you can conduct electrons, you can also conduct holes. And here's a summary of all of them, where you have an intrinsic semiconductor. So here you can just have like excitation, and the electrons can just move freely. If you have and then you leave behind a hole that's right here. So what happens when these things migrate? If you have an electron going one way and then you have the hole going another way, well, in order for the hole to go and migrate, what needs to happen is then if it migrates, let's say over here, right? Well, here in this example, it goes from here to here. That means then also an electron has to come and fill that hole. Right? Because these holes can't just like hop and occupy whatever space. The electrons have to come over and fill that, and now you have a new hole that's here. And that's the migration of holes throughout a lattice. And then for N-type and P-type, here for N-type, you have one extra, you have an extra valence electron, and so it's not bound to the lattice, and so it can freely move. Same thing with P-type, you have one fewer electron, so now your holes are moving. Okay. So in dealing with the energy states of extrinsic semiconductors, you can calculate out what exactly is going to be your conductivity sigma. That's dependent on both the band gap of your intrinsic material as well as the energy level of the donor state. So before we had, conduction band, valence band, and then we have a new donor state. Well, this has some energy level, Eg, and the difference between that the exponential of the negative of that divided by kT is related to your conductivity. So now if you plot the natural log of conductivity as a function of reciprocal temperature, what you see is something slightly different than just an intrinsic semiconductor, right? When we plotted this for an intrinsic semiconductor, all we saw was one behavior. We saw a linear line, and so that is indicating to us that there's one mechanism of hopping. But here, there's one mode, and then some range where your conductivity is not changing, and then another mode. So when your slopes are changing, that's an indication of different processes that are happening in your material. Right? So if it's like, say, for oxidation or something like that, for diffusion, what it's telling you is that probably there's a phase transformation or something else is happening in your lattice, and thus you have two different slopes. Here, you have two different slopes and also what's called an exhaustion range. So for this type of extrinsic semiconductor, what's happening is you have some sort of intrinsic behavior type, and then you have extrinsic behavior type. And here, what's happening is, if you're increasing temperature, it doesn't matter. In this range, it's not changing your conductivity whatsoever. One can also call that the saturation as well. So for every donated electron, so for N-type in the conduction band, you can have a range where your material is exhausted. You increase the temperature, it doesn't do anything. But then as soon as you pass some threshold in terms of temperature, it'll start behaving like an intrinsic type material where you increase the temperature and you'll increase conductivity. Okay. So increasing temperature this way, increasing conductivity this way. So at some point, your extrinsic material will behave like intrinsic properties if you go to high enough temperature. Same thing for P-type, you have saturation where all the acceptor states are filled. So that's this range right here where once they're all filled, as you increase temperature, conductivity doesn't do anything. Okay? Or it doesn't change. And then it goes into intrinsic type behavior. And your book has this, they just have it flipped around. So your book plots the x-axis here, the lower x-axis as temperature. And so this plot will just be the mirror image, but it's the same process, just the temperature, the x-axis is flipped. Okay. Rightio. I think, given the interest of time, we should just do the example that is here. So in terms of solving a system of equations, if you have the conductivity at a certain temperature, right, T1, and conductivity is 250, and now you have T is equal to 100 C, and the conductivity is increased dramatically. Right, and you're asked to solve for the band gap. Well, now you have to solve a system of equations very similarly to how we solved diffusion type equations, as well as getting diffusivity values, things like that. So you know that your conductivity is, there's going to be some prefactor. I write it as sigma naught, but sometimes you'll see it as A, or whatever letter is the prefactor. E to the negative Eg, your band gap, divided by 2 kT, K being Boltzmann constant. So if we write out the system of equations, we get I converted it to Kelvin already. Similarly, you don't know what the prefactor is. So this I already converted from 20C, and this I converted from 100C. Okay. So always remember temperature in Kelvin. So then if you solve the system of equations by subtracting one equation from the other, let's say ln 250 minus ln 1100, you get I should say this K is Kelvin, this K is not Boltzmann constant, okay? So, whereas this is KB, Boltzmann constant, the other K is Kelvin. So then you can move the numbers around and you get the band gap is 0.35 eV. And of course your Boltzmann constant is, if you use K of 8.6 times 10 to the -5 eV per K. So that eventually your energy term is going to be eV. Okay. Yes. The others, oh, you mean as it relates to carrier density and, wait, what's the other equation? Right. Well, here you don't know anything about the donor states, right? So ED is, this presumes that it is an intrinsic semiconductor because you wouldn't have ED if you didn't have impurity donors, right? And you don't have EA at the acceptor state because you don't know anything about the impurities. And since the question didn't say anything about it being an extrinsic semiconductor, and it didn't give you any information about the number of atoms that have been added, you could presume that it's an intrinsic semiconductor without any impurities. Okay, so I have about 5 minutes left, so I was going to go through an example of actually the extrinsic semiconductors where you have, let's say, antimony atoms being added into a germanium lattice. I don't think I have time to go through it fully in class, so I will just post the video to Carmen, or at least through the YouTube link, so we can go through that. In the 3 minutes that are left, I do want to just briefly go over the exam, because I promised you all that I would actually do that, so I will do that. So basically, the takeaway message is format will be the same. The change, an important change for you all, is that the uploading of your worksheet is now mandatory. Okay. There were quite a number of you that we had to track down and send very friendly reminders frequently to upload. And so to get around that, we're going to entice you, we're going to motivate you by giving you 5 extra points. Actually, it's not extra, it's just part of your grade. But it's your 5 points if you just upload your worksheet within 24 hours of the exam closing. I will send out an email as well, because I know we discussed in class, remind me somewhere else after an exam, but you can upload it before, and you definitely have to upload it within 24 hours of the exam. That is the biggest takeaway, that's the biggest change. Everything else will be very similar, and all the details are on the page. Okay? All right. Yes, one question. Do you still get 5 points for taking the factors exam? No, because it is exam 2. We figured you are now proficient at taking exams, so we shifted your 5 points over to uploading your worksheet. Okay? So you still get 5 points, quote, 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 but now it's for something else. All right. Have a good spring break, everybody.